All right, I think we're live. So hello everyone. Welcome back to yet another edition of Quarantine Thermo. So as always, I'll just explain the format to those of you who are new viewers. So basically, what we'll have is a kind of uninterrupted talk from Professor Murch, who we're very excited to have here. So he's going to talk for the next sort of 45 minutes to an hour, as long as he likes. And then at the end, we'll have a question and answer session. So if you have any questions about the talk, then you can ask them to Cater by just writing them in the YouTube chat window, and then I'll relay them to him at the end of the talk, and we'll have a nice discussion. Um, so, yeah, I think that's basically it. So let's move on to the science. So yeah, it's a great pleasure to have Cater Murch with us from Washington University in St. Louis. He's been doing some really incredible experiments over the last few years on superconducting circuits and quantum thermodynamics, and he's going to tell us about that today. So please go ahead, Cater.
All right. Good morning. Well, I guess it's morning here in St. Louis, but it's afternoon over there in Europe. This is my first time giving a talk over Skype in this way, so it feels a little odd to be speaking into the void. I don't have much chance for feedback from the audience, but I'll try to do the best I can. This is going to really be more of a colloquium level presentation. Those are the kinds that I like to see myself, so sort of big picture, hopefully not getting too technical into the details of the experiment, but giving you a flavor of what sort of stuff we're doing in my research group. I have this quote by Niels Bohr down at the bottom of my slide. If you're not confused by quantum physics, then you haven't really understood it. And I always like this quote because it gives me a little comfort that when I'm confused in my work, I know I'm really starting to get into the details, and that's okay to be confused. And for my thermodynamics talks, I've been including this quote from David Griffiths. And I quoted him as saying, "I never wrote a textbook on thermodynamics because it never made any sense to me." He was taught my undergraduate quantum mechanics classes at Reed College. And I was recently visiting the college and giving this talk. And I presented this quote to him, and he said, "I never said that about thermodynamics, maybe statistical mechanics, but I understand thermodynamics just fine." But in the end, he agreed that if he was quoted on the same page as Niels Bohr, he was okay with it. So it's now a verified David Griffiths quote on the slide there. So the outline of my talk is as follows. I'm going to say a few introductory remarks on sort of my take of what quantum thermodynamics is and how we're approaching this field and what we're trying to contribute to it. And then I'll talk about two studies we've done over the last couple of years that have been published, both of them somewhat recently. One is about a quantum Maxwell's demon experiment, and then the second is about trajectory reversal and the arrow of time. And I should have mentioned on this in the starting slide, but these are collaborative works. So the quantum Maxwell's demon project is something we did in collaboration with Eric Litz and Alessandro Romito. And the trajectory reversal and arrow of time project is something that we had a lot of help from Andrew Jordan's group at Rochester University of Rochester. Okay, so as we all know, thermodynamics is a field of science born in the study of macroscopic quantities such as heat and work for macroscopic systems. And these large systems, the quantities are so large that the fluctuations are irrelevant. But the interesting thing about thermodynamics, in some sense, is as you start to make smaller systems, mesoscopic systems, the quantities themselves become comparable to the fluctuations. And the questions in quantum thermodynamics really have to do with how do these quantities and these ideas developed for macroscopic thermodynamics extend down into the quantum regime, where we have different phenomena such as quantum fluctuations, there's quantum coherence, quantum decoherence, entanglement, measurement backaction. So what's the connection between these two fields? And I want to highlight a significant amount of work from Jukka Pekkala's group, who's really been forging quantum thermodynamics, really, in my opinion, from the sort of mesoscopic perspective. So thinking about single electron circuits at low temperature where the fluctuations are relevant, and trying to understand what does thermodynamics look like in this regime that sort of straddles into the quantum regime, but also can be connected to the sort of large system regime. So that's one approach to studying quantum thermodynamics. Another approach, which I'm participating in, is that of quantum information groups. So people who are normally getting funding and focused on building quantum computers in some sense, realizing thought experiments in quantum thermodynamics, sort of with this quantum information processing technology. So one such example is the work from Ferdinand Schmidt-Haller's group, where they built a single atom engine out of a trapped ion. So it's a sort of technology used for making ion traps and ion trap-based quantum computers, but now turned into a thermodynamics experiment. And so they're kind of coming at this question of what is quantum thermodynamics from different angles. So the most iconic example of thermodynamics and the role of information in thermodynamics is, of course, Maxwell's demon. And in this thought experiment, a demon measures the positions and momenta of various molecules and uses a trapdoor to let the hot molecules through and the cold molecules to stay on one side of the thing to generate a temperature difference without doing any work. And the reason this is interesting is because we have to take into account the demon is recording the positions and the momenta of these different molecules. And so there's some memory cost to that, and that sort of saves our thermodynamic description of this apparent paradox. So the point is that the demon highlights the role of information, and this, in some sense, allows the demon, you could think about it, the demon is highlighting the role of information, and that's uncovered in the sense that the demon is violating the second law of thermodynamics. So if we ignore the information, the second law is violated, and that tells us we're missing something important. So we're talking about information, and we're talking about cheating the second law. And so when we talk about information and cheating, it makes me think of a card game. So, and there's a really nice way to understand how we quantify information in thermodynamics. So let's say you have a shuffled deck of cards, and you want to guess which card is on the top of this deck. Okay, so the probability that say the 2 of clubs is 1 in 52. Right, but if you have a tendency to cheat at cards, and maybe when you're shuffling, you looked at the bottom card and saw that it was the Jack of Hearts. Well, then you know that the top card is not the Jack of Hearts, and therefore the probability that the top card is a 2 of clubs is now 1 in 51. So you've refined your information by looking at that bottom card, and we classify or quantify that information you've gained in terms of the difference between the unconditioned Shannon entropy and the conditioned Shannon entropy. So in this case, it's the log of 52 minus a log of 51. So some quantification of the information in terms of mutual information. Okay, so that's kind of how we think about information. Now, what about a quantum Maxwell's demon? So in the classical Maxwell's demon, we're thinking of these molecules as individual sort of classical particles. They have well-defined positions and momenta, and the demon can measure them. The disturbance of the measurement is something that we don't worry about. But a quantum Maxwell's demon might be a demon who's measuring molecules that are actually in a superposition of 2 different momentum eigenstates. So these start sorting molecules that are both swift and slow at the same time. And the question is, how is the demon going to measure the position and the momentum of these particles without colliding?
Sorry about that. I don't know why that happened.
No, it's no problem. Where do you want me to pick up?
So I think I managed to catch it just, yeah, so sorry everyone, the usual tech issues. I think I managed to catch it just at exactly the same place that I stopped you. So I think hopefully if you can just continue from where you were, it should be fine.
All right, so I'll go ahead and share my screen again.
Yeah, that would be great. Thanks very much.
Okay, can you see that?
Yeah, I can see that fine. Yeah, thanks.
All right. So I was saying that there have been many experiments that are exploring the physics of Maxwell's demon at the energy level corresponding to single energy quanta. So these are experiments with cold atoms, molecular ratchets, colloidal particles, single electrons, photons, and so forth and so on. And so they're getting at some of the physics of Maxwell's demon, but mostly in the fact that they're working at these really low energy levels where fluctuations are relevant. But I would argue, based on what I was saying in the previous slide, that really a true quantum Maxwell's demon would involve some sort of coherences. And so these experiments, while they may have involved coherences, the demon's measurements are destroying those coherences. And so what we're interested in is a quantum Maxwell's demon where the role of coherence, not destroyed by measurement, plays some sort of significant role. That's what I'll tell you about. Okay, so in order to do this, we're going to go back to our thought experiment of a Maxwell's demon, and we're going to make this as simple and as small and as cold as possible. So let's take our many particles in a box, and let's take that down to the level of one particle in a box, okay? And then let's cool the system so that the particle might occupy just one of the two lowest energy levels of the box. And so that's now a pseudo-spin half system. And so we'll just think about the physics of spin half systems and the physics of measurement. So this is then a chance to talk about the sort of real basics of measurement and spin half, all the way going back to the discussions in David Griffith's seminal textbook for undergraduates. Okay, so imagine you have a spin half particle and you subject this to a sequence of measurements. So you can measure the z component of the spin, the x component, z, x, x, z, x. So we're sending the spin through, say, some gauntlet of Stern-Gerlach apparatuses. And each of these measurements is going to give us an eigenvalue. So the z measurement gives us +1, so we know the expectation value of sigma z is +1. Okay, but then the x measurement says -1, so now we know the expectation value of sigma x is -1. And the z measurement says -1, okay, so now the expectation value of sigma z is -1, and so forth. So the results of these measurements can be sort of interpreted as time evolutions of the expectation values of the Pauli operators. Okay, so we have a time evolution of these Pauli operators. Okay, but let's make this a little more general and instead consider a sequence of generalized measurements that could be given by some Krauss operators, M1, M2, M3, M4. Each of these gives a measurement result, result 1, result 2, result 3, result 4. And we're interested in, say, how does the quantum state, which we might describe using a density operator, and so here's one component of the density matrix, rho 0, 0, how does that evolve in time based on the outcomes of all these different measurement results? Okay, so this is the sort of the most general case of measurement leading to a change in our description of the state, so our density matrix description of the state, and the time evolution of that quantum state is what we call a quantum trajectory. So having introduced this idea of a quantum trajectory in sort of abstract form, the idea of a quantum Maxwell's demon is going to be that quantum Maxwell's demon uses machinery of quantum measurement and quantum trajectory tracking to make measurements of some system, and then having acquired information about the system, the demon will do something with that information, perhaps extracting work or generating a temperature difference, one or the other, or both. Okay, but the tricky part is that the quantum system we're considering can be in a superposition of energy states. So we might start off in some initial superposition of these two energy eigenstates, alpha times psi 0 plus beta times psi 1, and there's some measurement, there's some dynamics. At the end of some time, we may end up with a different superposition of energy states, alpha prime, beta prime. And so the question is, what is the change in energy in the system when the energy is not necessarily well defined? And this is relevant because changes in energy can be interpreted as work. So if the demon starts off with a system of one energy and it ends up in a lower energy, you can interpret that as work extracted from the quantum system. Okay, so the way to characterize work changes, work done on or work extracted from these quantum systems is typically performed with something called the two-projective measurement scheme, or a two-point measurement scheme. And so here's the basic idea, is what we're going to do is, rather than try to get into the discussion of talking about how much does the energy of our system change when we go from this superposition state to this indefinite energy state, we'll actually just make projective energy measurements at the beginning and the end of the protocol, therefore projecting the system onto its energy eigenstates. And so we can say, okay, the energy increased by 1 quanta or the energy decreased by 1 energy quanta. Okay, so we're looking at transition probabilities between energy eigenstates. So let's say at time t equals 0, we measure the system to be in the ground state, n equals 0. We let it evolve, and at the end of the protocol, we measure again with a projective energy measurement and find the qubit to be in the excited state here. Okay, so that gives me something like a transition probability, P01, the probability that starts in state 1 and ends in state 0, and 1 quanta of energy is extracted. Okay, and then we can interpret that as work if we'd like. So we're going to use this tool to quantify energy changes in our system, and we The advantage of it is that we really use talking about definite changes in energy between energy eigenstates. Okay, so then let's move on to how we're going to do this in the experiment. So here's sort of a theorist description of the experiment. We have a qubit. It's a pseudospin half system, so it has a Hamiltonian proportional to this Pauli operator sigma z, and an energy scale set by that qubit frequency omega q. And we're going to couple this qubit to a single mode of the electromagnetic field, so a microwave cavity. Okay, so it has a Hamiltonian omega cavity, A dagger A. And the coupling between these two systems is this dispersive interaction. So there's some energies, the interaction strength chi, sigma z, A dagger A. So what this, you can think of this as, it's a qubit state-dependent frequency shift of the cavity. So the cavity energy is changed as we change the state of the qubit given by this Pauli operator sigma z. Okay, so in experiment, what this looks like is we have the qubit circuit is a transmon circuit. It's fabricated from aluminum deposited on silicon with a Josephson junction shunting two capacitors, or a capacitor. And we embed that qubit circuit inside a three-dimensional microwave cavity that defines this cavity here. Okay, and so we also have on this cavity a few ports, and we can drive both the qubit and we can drive the cavity. So we drive the qubit with a Hamiltonian omega Rabi sigma y over 2. What this does is this induces Rabi oscillations, causing the qubit to oscillate between its ground and its excited state. So just a standard Rabi drive is what we call it. And we also drive the cavity. Now we're going to drive the cavity with a coherent state of the electromagnetic field. And so I'm plotting that here on the quadrature space of the electromagnetic field with these two quadrature amplitudes I and Q, or you can think about them as like the position and momentum of the harmonic oscillator description of the electromagnetic field. This drive, just given by this arrow here, has some sort of ball attached into it, and this just indicates the quantum zero-point fluctuations of the electromagnetic field. So it's a coherent state, a minimum uncertainty, somewhat classical drive on this cavity. So when this drive impinges in the cavity, the qubit state-dependent frequency shift of the cavity, given by this Hamiltonian term here, results in a qubit state-dependent phase shift on the coherent state that passes through the cavity. Okay, so the phase shift may be positive if the qubit happened to be in the excited state, and it may be negative if the qubit happened to be in the ground state. Okay, and you can see there's, again, some uncertainty in this, and that uncertainty comes from both added classical noise in the imperfection of our detection, but also from the fundamental quantum noise in the state that we sent in originally. Okay, so then we take this this signal that transmits to the cavity, and we're going to demodulate it because you can see the I quadrature is somewhat proportional to the shift in the state. So it's going to tell us if it was in the ground state or the excited state. So we'll demodulate that and digitize it. And so we end up with a measurement record. And the measurement record, for example, looks like this. It's a noisy trace. The noise mostly originates from the fact that we have quantum fluctuations in the measurement process. Okay, so I take that measurement trace, and what I'm going to do is I'll think about each one of these digitized measurement values as corresponding to a different measurement operator, M1, M2, M3. And so each one comes up with a result, result 1, result 2, result 3, and so forth and so on. And I can go through the sort of mechanics of what the interaction is between the qubit and the cavity, and I can write down actually a measurement operator for this, this process. So this measurement operator actually has embedded in it the unitary evolution due to the Rabi drive on the qubit, but it also has this sort of this term here, which depends on the measurement result. And so the mechanics of POVM measurements is such that we can update the state given by our density operator rho by applying these measurement operators, and that gives us a next state rho k plus 1. So if we start off with an initial state, we can then create a piecewise continuous trajectory of density operators, and that's our quantum evolution of the state, our quantum trajectory. It's sort of more intuitive and more useful to plot this quantum trajectory in terms of the Pauli expectation values, sigma x and sigma y. So that's what we show here. So z is the expectation value of sigma z, x is the expectation value of sigma x. And so in the solid lines, we see these oscillatory trajectories as the expectation value of sigma z goes from +1 to -1, so the ground state to the excited state, and the expectation value of sigma x goes from 0 to -1 and so forth and so on. So you can see this oscillatory behavior, and that oscillation is due to the fact that we're driving the system to undergo Rabi oscillations. But you'll also see that these trajectories are rather noisy. And that noise comes from the fact that each one of these measurement values updates a state in a stochastic way, shifting it either up toward the excited state or down toward the ground state. So we have these sort of distorted, noisy traces. And this is a single quantum trajectory based on one experimental run of the experiment. Now, we might be concerned that that single quantum trajectory is not the exactly accurate description of our quantum state. So we have some trick where we do quantum state tomography to verify that really is what the state is doing. So we can see that all these kinks and bumps and wiggles really do reflect how the quantum state is evolving. Okay, so this is technology that we developed now almost 7 years ago. And we've spent the last 7 years applying this technology of tracking quantum trajectories and superconducting circuits to sort of every area of physics where we felt like it has some relevance. And so the thing I'll tell you about today is applying this to the context of a Maxwell's demon type experiment. Okay, so again, we want a quantum Maxwell's demon. So to highlight the features of that, let's contrast what I think of as a classical Maxwell's demon to a quantum Maxwell's demon. So a classical Maxwell's demon thinks about, so this is a two-state system, but we can think about this as two definite classical states, say a lower shelf and a upper shelf. And so the classical Maxwell's demon would describe this two-state system with a density matrix that just has diagonal elements, and off-diagonal elements are zero. Okay, so just think of probability of 1, probability of 2, but no sense of superpositions of these states. Okay, and so in the sense, when the classical demon makes measurements on the system, there's no disturbance. He's just revealing the unknown states behind those probabilities. Okay, in contrast, the quantum demon has actually read to the chapter in Sakurai where it describes the density matrix, and we know that we can have these off-diagonal terms that have to do with coherences between these two energy eigenstates. And so in this sense, the role of disturbance in the measurement will be prominent. That has to do with entanglement between the quantum system and its meter, and we'll ultimately find that information can be lost in the quantum demon in a way that it can't in the classical demon. Okay, so again, here's the protocol we'll do. We'll start with an initial quantum system in some thermal equilibrium. So it's described by some temperature. And then the demon is going to make quantum measurements on the system while it's undergoing quantum coherent dynamics. And then the demon, using the information gained in those measurements and using the whole machinery of quantum trajectories, the demon will extract work from that quantum system. And in order to quantify the work the demon extracts, we're going to insert these projective energy measurements right before the demons get started and right after the demon is done, because that allows to tell us exactly how many quanta of energy the demon extracted. Okay, so that's the abstract description of the experiment. Here's the same thing in pictures, something made by my brilliant student, Matthew Nagalu, who's now a postdoc. So we start off with this initial thermal state. Okay, so I've defined things such that the ground state is at the top of the block sphere. So this is some state that has some finite probability to be in the excited state, but again, it's diagonal in the energy basis. We're going to then make that first projective energy measurement to determine what the initial state of the qubit is for our two projective measurement protocol. Then the demon is going to track this quantum state. So the demon's making measurements while this quantum state is undergoing some sort of unitary Rabi drive evolution. At some later time, the demon's state of knowledge about the state can be summed in terms of its expectation value of sigma x and sigma z. The demon then applies a unitary rotation to the qubit to extract the work, to put that in the ground state. And then we can apply that second projective measurement to determine in the projective measurement protocol exactly how much energy was extracted from the qubit. Okay, so these two projective measurements allow us to talk about the work distribution for the qubit. So first, let me show you this work distribution when the qubit does not, when the demon does not do any feedback to extract the work. So the demon is just measuring the state, but in the end doesn't apply the unitary rotation to try to extract work from the system. Okay, so we have these three types of transition probabilities. We can go from the excited state to the ground state, or the excited state to the excited state, ground state to ground state, changing no energy in no way, or we can go from the ground state to the excited state. And so this distribution has folded into it the initial probability distribution of the qubit energy eigenstates. And so you see it's just unlikely initially that it's in the excited state because this is at a very low temperature. Okay, so when the daemon now applies feedback to try to extract work from the qubit after measuring it, we find that this different feedback distribution, this different work distribution. So we have here, it's actually more likely that it goes from the excited state to the ground state, and it's less likely it goes from the ground state to the excited state. So you could say that there's work extracted due to the feedback, in that the transition probabilities are shifted, favoring the energy of the qubit being lower or colder at the end of the protocol. Okay, so that's the work distribution extracted from the projective energy measurements. But we also have a record of what the daemon does in every possible measurement step. And so the daemon is applying a rotation, and so that rotation takes the state from different values of the energy. So if we think about the expectation value of sigma z being proportional to the energy, the daemon is actually extracting a continuous amount of energy at different value each time. So you have two different work distributions, and it turns out that these two different work distributions actually have to average to be the same thing. And this is due to something called the law of total expectation. So the expectation value of a conditional expectation value is the same thing as the expectation value of that thing. Okay, so the idea is that the daemon is making measurements and using that information. And so if we don't pay attention to the information the daemon's using, you can think about the daemon as cheating, just like we thought about cheating in that card game earlier on in the talk. Okay, and so that cheating is against the rules. What rule does it violate? It violates the second law. And we're going to state the second law in terms of the Jarzynski equality, which relates changes in free energy to the work applied to a system, average over that work distribution. So you all recall that the change in free energy tells us about the ability of a system to do work. And the standard description of the second law is that the change in free energy is always less than the work applied to that system, but with an equality for a quasi-static process. And Jarzynski's equality allows us to calculate free energy changes by looking at the distribution of trajectories for where we have applied work along those trajectories. Okay, so what does it look like if we try to characterize this daemon's process in terms of the second law? Well, there's a lot of pieces that go into this, and so let me walk you through this slide. So in step 2 of our protocol, we do this projective measurement. In step 5, we do a second projective measurement. So these give us these transition probabilities. Okay, so here's a case where the work done was 0. Here's a case where the work done was 0. Here's a case where work done was 0. Here's a case where the work done was 1 quanta, and so forth and so on. So we can take the work distribution, put that in the exponential here, and we average over this whole distribution of work. And that gives us the Jarzynski, the one term of the Jarzynski equality. Now, because this protocol, the initial and final Hamiltonians are the same, we expect the change in free energy to be 0. So Jarzynski's equality would say that e to the beta work averaged over the work distribution should be equal to 1. But in fact, we find that this quantity is in fact not 1, it's something like 2. Okay, so indeed, the daemon is violating the second law, and that's because we failed to take into account the information the daemon has in doing this feedback protocol. Okay, so if you just read through the literature another 10 years later, we'll find that there's a discussion of a generalized Jarzynski equality where the information and feedback is taken into account. Okay, so this is something that we read about in a paper from Sagawa and Ueda. So the basic idea is to introduce an information term I. And as I told you in the beginning of the talk, normally we think about this information in terms of the mutual information. Okay, but we have to think about this slightly differently in the context of this quantum evolution, because the mutual information is just traditionally thinking about the probabilities that the qubit occupies the energy eigenstates. But at the end of the evolution, it may not be diagonal on the energy basis. And so if we just think about those probabilities, we're throwing information away. So the idea is that we're going to redefine the mutual information. We'll call it something like the information exchange, where we look at the end of the protocol, the probabilities in the basis Z prime, where the qubit state is diagonal. That is, after some evolution, we have some state. It's not diagonal in the energy basis, it's diagonal on some other basis. So we'll look in this basis here. So you can see this is related instead to the von Neumann entropy rather than the Shannon entropy of the qubit. Okay, so we can now calculate this generalized Jarzynski equality. So again, we look at these transition probabilities, but we also take into account the information accumulated by the daemon along each trajectory. Okay, So that involves adding that piece into the calculation. And what we find is that here, when we take the information into account, we see that the measurements we have are very consistent with 1, corresponding to the demon obeying this generalized Jarzynski equality. Okay, so this information term that we introduced to sort of save the second law is something we have to really introduce to save the second law. But now that we have it, we can say, well, what is going on with this information? How does it change in time? What does it increase? Does it decrease? And so forth and so on. Okay, so the information exchange depends on 2 different types of stochastic quantities. One is the probabilities in the z and z prime bases, okay? And the other is it depends on the individual trajectories given by this record R, okay? And so if we average over those probabilities in the z and z prime bases, we have the information exchange over time along single quantum trajectories. So this graph here shows exactly that evolution in time. One quantum trajectory for the information exchange is shown as a dashed line here. And so you can see it's stochastic. It has stochastic behavior commensurate with the stochastic evolution of the qubit. This whole forest in light green in the back shows just sort of the range of different values of information exchange that we see. Oh, so it's just the result of 1,000 different experiments. And the solid curve here indicates the average over all of those, that whole distribution. So right away, you might notice that the information exchange in this case is generally negative. And that may seem surprising to you if you're familiar with the fact that classical mutual information is always positive. So how is it that we're ending up with negative information? What's going wrong in this quantum case to have a negative information exchange? But before I tell you what's going wrong, let me show you, convince you that why the classical mutual information should always be positive. So I'll go back to this card game example, where we're trying to guess in a shuffled deck, what is the probability that the top card is a 2 of clubs? Well, it's 1 in 52. Again, if we look at the bottom card, the probabilities are gained information. But if someone else looks at a card in the deck, that doesn't change our probabilities. Our probability that the top card is 2 of clubs is still 1 in 51. So someone else's measurements don't seem to hurt our information. And this is even true if we start with a stacked deck. So I've shuffled things in such a way that the 2 of clubs sits on the top of the deck. I know with certainty that it's the top deck. Could look at the bottom card again, it's not going to change my information. Someone else looks at a card in the deck, again, it doesn't matter because I already know the top card is the 2 of clubs. Okay, so that's classical mutual information is always positive. The quantum case is in fact not so. So let's say I take a quantum case where I have a stacked deck and I've actually stacked the top card to be an equal superposition of all 52 cards in the deck. So it's 1 over the square root of 2, square root of 52, the 2 of clubs plus the 3 of clubs plus the 4 of clubs and so forth and so on. I know exactly what state the top card is in. It's in this complicated superposition state. Now, if someone else looks at a card in this deck, well, all of a sudden they see it to be, say, the Jack of Hearts. That changes the superposition of the top card. So I lose information when someone else looks at a card in the deck. Okay, and that's exactly what's going on in this case of information gain and loss in our Maxwell's demon protocol, is that there's decoherence of the qubit, or there's other measurements of the qubit that are then contaminating the superposition state that the qubit was in. So we find there's actually transition from having information gain to information loss, and this depends on the initial purity of the state. So if we start with an initial high temperature qubit, the state is very impure, there's lots of information to gain. But if the initial state is very pure, this temperature is very low, then in fact there's just information to lose. Okay, so we see a transition from information gain to information loss. And this sort of highlights the challenge of quantum Maxwell demon type protocols, is because coherence is such a fragile thing to maintain. You have to worry about losing information. It's also the challenge of making quantum computers in some sense. So we've been, since performing this study 2 years ago, we've been slowly working toward extending the study and trying to think about the richness of this problem. And one aspect of that is in this quantity, which we call efficacy. It's just a calculation of e to the beta work, so that left-hand side of the Jarzynski equality when we ignore the information. And this is a nice quantity because in some sense it's a dimensionless, more information theoretic quantity. And we see that in the feedback protocol, we get efficacies that are approaching, but limited to 2. And that's due to the dimensionality of the Hilbert space of our qubit. So we can imagine extending this to larger systems, showing that larger systems allow for sort of more violation of the second law in some sense. It's also an interesting process because the work, along with this efficacy, those things are not observables. And so they really have to do with correlations of the qubit. So we actually have to track the full quantum process in turn to maximally extract the efficacy, or in some cases to maximally extract the work. So it gets into sort of a richness of quantum trajectories that goes beyond just the description given by the state. Okay, so we're working on experiments with qubits. We're thinking about quantum processes. We're thinking about the challenges of feedback control in these larger Hilbert spaces, and so forth, and so on. Okay. But as I wrap up my discussion of this one experiment, I want to say something maybe a little more provocative, is you can ask the question, what is information? And in our experiment, our experiment gives us a way to define what we mean by information. Information in our experiment is the thing that salvages the second law. Okay, so the classical mutual information did not salvage the second law, so we had to adapt that to be this information exchange, which is really a change in von Neumann entropy. And so the only way to make sense of what the daemon is doing in a thermodynamic way is to consider the coherences of this quantum state, of the working medium that the daemon is using. So it forces us into a quantum description of what is information, what is this description of the state. And so I have this sort of hope that we can use these sorts of thermodynamic thought experiments to force upon quantum systems certain aspects of quantum mechanics. That is, you can think about, we have this quantum system, it's extracting work, we're doing quantum measurements, we can learn the nature of quantum mechanics just from thermodynamic principles. Okay, so that takes me to the third part of the talk, where I'm going to talk about a different projects which is getting at, again, the questions of information and entropy from a different angle. And this has to do with path probabilities and the arrow of time. So taking us back to my description of the measurement process and the measurement record. Okay, the measurement record is the stochastic values corresponding to the digitization of our measurement signal. And what I told you is that we can take those measurement records, each one of those corresponding to a Krauss operator, M, and we can use that to update the state. So we get a piecewise continuous trajectory, which here I'm showing as one element of density matrix, rho 0, 0. Okay, so the measurement allows us to calculate the quantum trajectory. But at the same time, the measurement results are sampled from a probability distribution that depends on the state. So the measurement affects the state, and the state affects the measurement. And it's this sort of circular nature of measurement and state being intertwined with one another that makes the quantum measurement process so rich. Okay, so the fact that those two things are related allows us to define a path probability density. That is, here's my state evolution, which I'm plotting in terms of expectation value of sigma z. And I'm going to squish that down so I can plot on the same axis the measurement results we have. That is, the measurement results are sampled from a Gaussian distribution whose mean value is given by the expectation value of sigma z. And so each measurement result, of course, comes from a certain probability density. And so from this approach, I can calculate the probability density for a given measurement sequence of measurements having known state. And the reason why I'm interested in path probability is because path probability can ultimately be related to entropy. That is, consider some system where it's a small system, and we want to understand what is the change in entropy of the system. Well, that change in entropy of the system, it could be fairly easy to calculate because we can look at the probability of the initial state and the final state, and maybe the system is small enough that we can really assess those probabilities, so we can talk about the change in entropy of the system. But let's say the system is then interacting with some complicated environment, and we want to know the change in entropy in the environment. Well, that's more challenging because the environment has so many degrees of freedom, it's probably impossible to know exactly what state it's in, or to know how many microstates correspond to the state that it's in, and so forth and so on. And so the idea is that we can calculate the change in entropy in the environment by looking at the path probability. That is, we're going to compare the probability of the forward path to the backward path. It's just like when I spill my coffee on the table, it's an entropy producing act, because it's very unlikely to have the coffee on the table, come back up and jump into my cup. So we can use this sort of path probability, which one is more likely, forward or backward, that is the arrow of time, to assess the change in entropy in the environment. Okay, so that brings the question, can we apply this sort of idea of assessing entropy production in the environment to these quantum measurement dynamics? So that's what we'll talk about now. So we're going to get even more deep into the microscopics of our measurement update. So if we have some initial state here, initial pure state, call it rho sub k, given that state, the measurement result is going to be sampled from a distribution that includes some probability corresponding to the measurement results we get for the excited state, and some probability that's slightly larger for the measurement results we get for the ground state. Okay, so if we sample a result r sub k, what that tells us is that we're getting a result that's more likely to get if you happen to be in the excited state. So in the Bayesian reasoning, this causes an update in the state that shifts the state closer toward the ground state, closer to the top of the block sphere. Okay, so measurement results, the measurement back action is such that positive measurement results push the qubit state up, negative measurement results push the qubit state down. Okay, so to reverse this process, what we have to do is we have to change the sign of the time step delta t that undoes any sort of unitary evolution that we're applying to the qubit. And we also change the sign of the measurement record r. Okay, so we apply the measurement result minus r, and that'll take the state rho k plus 1 back to the state rho k. So we're looking at these piecewise continuous quantum trajectories where we start with some initial state and we use the measurement results at each step to update to the next state. So the result, the state at rho k, at time step k, gets updated by the measurement result that comes right after that to give you the next state. And now we can imagine stepping backwards in time from the final state at each point, applying this time reverse measurement operator, which involves, again, changing the sign of delta t and changing the sign of the measurement record to step back to have the same exact sequence of states. And the essence of this is that the probabilities of these two measurements can be different. And so we'll end up with different path probabilities, forward versus backward. So that's the theoretical idea. When we try to apply this to experiment, we find that it's actually quite difficult to do. And the problem is due to measurement inefficiency. So again, our cavity output has this qubit state dependent phase shift on the probe in the cavity, but that we don't manage to detect all of that signal. In fact, some of that signal is split between us, our detector, and some place where it's absorbed along the way. And one way to model that finite efficiency is with a beam splitter that sends the signal to us with efficiency eta, and it sends it to some other observer who we'll call Bob with efficiency 1 minus eta. And this is a problem because whenever we have a beam splitter, it allows additional quantum noise to enter in to our measurement channel. So what we detect is actually a mixture of noise and real signal that we're interested in. Okay, and this is a problem because normally what we do is we just average over the different possibilities of this noise, giving to rise to some sort of impure dynamics, ultimately to the loss of information I discussed earlier. But the measurement reversal that we discussed on the previous slide only works for pure states. And so the idea is that Bob's measurements also affect the trajectories. And so we have to somehow estimate what Bob measured. And the way we're going to do this is by unraveling quantum trajectories. We're going to come up with a hypothetical observer, Charlie, who has access both to our measurements and to Bob's measurements, and can sort the signal from the noise so as to construct a real quantum trajectory for the system, for the pure state. And we do this by modeling the beam splitter in this time segmented fashion. So our record is a bunch of values, R0, R1, R2, R3. Bob's record is some other thing here. And we just we assume that the beam splitter takes different configurations, directs a signal to us at some time steps and to Bob at other time steps. When it's going to Bob, we get noise and vice versa. So we can take our record and Bob's, some hypothetical record for Bob, and we can then sample a possible record for Charlie, the true evolution of the state. We don't know exactly what that is, but we can sample over all possible records for Charlie to determine the sort of true quantum evolution of the system. There's a process known as unraveling the Lindblad evolution of the master equation. Okay, so this turns out this unraveling depends on the measurement basis that Bob uses. So if Bob measures in the same basis we have a bunch of different possible unravelings. Those are shown in blue for pure state quantum trajectories. When we average those, we of course get a trajectory that matches our individual original trajectory that we sampled. But the true state of the system is actually spending more time towards the eigenstates of the measurement operator. But if Bob measures an incompatible basis, this actually sort of ends up changing the phase of the quantum state. And so we end up with the trajectories that tend to diffuse all over the Bloch sphere, as shown here. Okay, now what we define as the arrow of time, we could think about this lots of ways, where we're going to ask how correlated is our observed record, our measurement record, how correlated is that to Charlie's state, the true state of the system? And then we'll average over all the possible unravelings for Charlie to get some sort of average arrow of time, our best guess for the arrow of time in this process. Okay, so again, that we have these piecewise continuous trajectories. We define this quantity Q, an arrow of time quantity. It's like a information entropy. It has to do with the probability of the forward record versus the backward record. And we can just straightforwardly calculate this from our states and our measurement records. And we average over the possible states. So the states are Charlie's state, and the records are our measurement records that we obtain. Okay, so we do this for, say, some 10,000 experiments, and for each quantum trajectory, we calculate this quantity Q. And I'm plotting for you a histogram of the arrow of time quantities Q versus Q. Okay, so we see oftentimes values Q that take a value of 2. We see sometimes I have an arrow of time quantity that's 0. It means it's just as likely that the quantum trajectory is playing forward versus playing backward. And sometimes we see value of Q where the quantity is negative. So we see sometimes that the quantum trajectories appear to be going backwards in time, or the backwards evolution is more likely than the forward evolution. Now, it turns out that because there's 2 different possible bases for Bob to measure, and we can have 2 different sorts of arrows of time. And so this allows us to sort of place a bound on it's either this solid curve or this dashed curve or somewhere in between. So we kind of have these error bars in our estimate for the arrow of time quantity. Okay, so I can look at that those sorts of bounds on the arrow of time quantity versus evolution time. So for short evolution time, it's somewhat a Gaussian distribution centered towards 0. And as time goes on, this Gaussian broadens and moves to larger values of Q. Okay, and this evolution should be described by something called the detailed fluctuation theorem, which tells me the probability of getting an arrow of time Q pointing forward compared to the quantity of probability of getting an arrow of time minus Q that points backwards goes like e to the Q. So it's much more like for large quantities of the arrow of time, for like Q equals 4, it's overwhelmingly more likely that we have the forward arrow of time than the backward arrow of time. And we see that this detailed fluctuation theorem is actually obeyed for small values of Q, but as you go to larger values of Q, we see that this detailed fluctuation theorem stops continuing to be valid. And this breakdown of this detailed fluctuation theorem is due to the existence of something called absolute irreversibility. And we can highlight this effect by going to a special case, which is that of semi-classical measurement. So this is a case where we just prepare a eigenstate plus X, so superposition of the ground and excited states. We turn off the Rabi drive, and we just watch as the quantum trajectories collapse toward the ground or excited state. So it's just collapse of the wave function without any additional unitary evolution. This is a special initial state because it's unstable against the measurement. It's going to be projected into one eigenstate or the other eigenstate. So it's sort of like a situation where you have an ideal gas in a container, and you put all the molecules on one side and let it free expand. The entropy just has to increase in this case. And so that's what we see here. We see in no cases a negative Q. The arrow time never can go backwards, but in fact always goes forward. So that allows us to quantify this effect of absolute irreversibility, which comes from just sort of the looking at this average of e to the minus Q. So we can study this absolute irreversibility in this way. Okay, so I've almost used up an hour of time, and so let me summarize what I've told you about, and thank some of the collaborators and the students who've done the work. I still told you about a project where we studied a quantum Maxwell's demon with weak measurement. This is something we published now almost 2 years ago. And we're interested in extending that into sort of more complex quantum systems, to thinking about quantum processes and how to really get into the details of this process. And we're doing that by looking at larger Hilbert spaces and so forth. And then I told you about this project where we're studying an arrow of time and fluctuation theorems for continuous measurement. So by looking at arrows of time, but forward versus backward quantum trajectories. So the key personnel in all this work is Matthew Naivalu, who's now a postdoc at MIT, Patrick Harrington right here, who's just accepted a job as a postdoc at MIT, so he's also going there. And Xingri Song is the younger student just starting off on taking over these projects. Again, we work with Andrew Jordan on this Arrow of Time project, and Alessandro Romito and Eric Lutz on the Maxwell Demon project. So with that, I thank you for your attention, and I'll be happy to take questions over the chat.
Thanks very much, Keita. That was really interesting. So yeah, we've got lots of time for questions. If you have questions, just write them into the YouTube chat. So we've already got a question from Junjie Liu. I'll just bring myself back in. Junjie, he asks, does this dispersive interaction between the qubit and the cavity require a large frequency detuning?
Yes. So the interaction between the qubit and the cavity there's a resonant interaction G. So if we make the qubit and the cavity resonant, typically that resonant interaction energy scale is something like 100 megahertz. So we need to have a detuning between the two frequencies that's large compared to that, something like 2 gigahertz. So in practice, if you like experimental units, the qubit frequency is say 4 gigahertz, and the cavity frequency is 7 gigahertz. And that gives us an interaction strength chi, which is on the order of a few megahertz. So yes, they're dispersive interaction, meaning that they're different frequencies, so they don't actually exchange excitations.
Okay, thanks very much. So don't be shy to ask questions, guys. But there's a bit of a delay, so we might have to wait a little bit for some to come in.
That's fine.
So maybe I can just ask you something about this arrow of time experiment, which is really interesting. I really like it. I was just wondering, you showed these plots of like the distribution of Q for the different kinds of measurements. Like, do you understand? I mean, could you explain why? What causes this difference between a measurement of? The different measurements of this is different measurement bases of Bob, I guess, right? Is that what it is?
Yeah, that's right. So this is so you can see that the Bob has these two choices of measurement bases. One is this measurement Z. That's the same measurement basis that we're measuring in. So in that sense, Bob's measurement. So we see in that case the arrow of time is sort of broader. It's as if we had measured for longer or something. And what that means is that his measurements are sort of contributing to Charlie's state to spending more time toward the extremal values of the qubit, of the expectation value of the measurement operator. So the more extremal the values of the qubit state is, the stronger its correlation with their signal is, either positive or negative. And that causes it to spread out. So it's just that the values that the qubit Pauli expectation value take are more extremal on average when Bob reinforces our measurement value. If Bob measures in other bases, in fact, he doesn't contribute anything to, the state's not spending more time near the eigenvalues of the measurement operator. And so he actually doesn't contribute at all to our arrow of time. So it's as if we had measured with 100% efficiency in that case. So I hope that makes sense, that Bob is just pinning the state toward the ground in excited state more when he measures in the same basis as us.
Yeah, thanks. Yeah, that makes sense. Very interesting. Okay, so I think we have a question from Ottavio Molitor, who says, "Thank you very much for the talk, Keita. When you showed the occurrence x q, I guess that means occurrence by q plot with the time evolution of the distribution. Is it related somehow to the coherence time of the transmon?"
So my understanding of the question is, looking at this distribution, what is the role of the coherence time of the transmon? And here's what I can say about that. So the reason we have to do this unraveling trick, hypothesizing another observer, Bob, that's measuring our qubit, is because that corresponds to, can be thought of in some sense as a finite coherence time of our qubit. One way to think about a decoherent qubit is that someone else is in there making measurements, or it's being entangled with some other degree of freedom in the environment. We can call that some other observer. And so the extent to which these two curves are different corresponds to both our inefficiency of the measurement that we're making, but also to the effects of sort of additional decoherence of the qubit. And so all of the sort of non-idealities of the qubit are chalked up to sort of our inability to get these two lines to match, to become really close to one another. So in my opinion, it's actually quite impressive that the changes in these distributions is rather small, considering all the possible things that Bob could have done one way versus the other way. So we can exactly think about these two limits as coming from the decoherence of the qubit and not knowing exactly what that process is.
Thanks. Very interesting. Yeah. So actually, what is the typical kind of coherence time, or I mean, what's the kind of measurement rate that you can achieve in these experiments?
Yeah. So if we do no measurement at all, the decoherence time of this qubit is on the order of 15 microseconds. So it's, in my opinion, that lasts quite a long time when the typical time scales or gate times are measured in nanoseconds. So 15 microseconds is how long it stays quantum coherent. But when we make these measurements, we actually want our measurement interaction to dominate that background decoherence. And so we're operating with a measurement strength that corresponds to a decoherence time of about a microsecond or much less than that. And so there's a decoherence time scale that corresponds to, say, 1 microsecond from measurement, and an additional one that corresponds to 1 microsecond from the lost signal, because the quantum efficiency is 50%. So here I'm talking about time scales, but really we should talk about rates. So the decoherence rate is 1 per microsecond, and our measurement rate is 1 per microsecond. And so together, those make a decoherence rate of 2 per microsecond. So we're working, factor of 10 away from the background decoherence of the qubit. So we can really neglect that as an effect.
Okay, thanks very much. So we have a interesting question from Michael Moskalets. He says, "Thank you for the nice talk. The arrow of time, can this arrow be rotated? And if yes, what does it mean?"
Very interesting. So, so we have this arrow of time and it points forward or backwards, but what would it mean if I don't know what that other axis would be versus forward or backward. So I don't know what that would mean. So if you have an idea what that would mean, you could suggest it, but that would take some very creative thinking to think about the arrow of time, rotating it into a complex plane. Maybe that's the way to think about it. Yeah, it makes me think, to be really sort of crazy spitballing, you say, okay, we have this, the arrow of time is a real quantity. It's forward, backward, but now we have to have some sort of, we want to rotate it. We could think about the arrow of time being complex. What does it mean to have a complex arrow of time? It means that this quantity Q is complex. We have to get that out of these probabilities. And we could try to think about a way that would make some sense, but I can't do it off the top of my head. So, but a creative question for sure.
Maybe I can ask, instead of rotating it, but what can one do to actually, perhaps you've already touched on this and I haven't understood, but is it possible to do something where you really reverse the kind of measured arrow of time? I guess there should be some sort of daemon that could do this, right? Would you be able to implement this in your experiment?
Right, absolutely. So this is just sort of free quantum measurement dynamics of the qubit and look at the arrow of time, but we've been interested in how does this arrow of time change with feedback protocols? So now instead of just measuring and studying the dynamics of that, we're actually measuring and doing things to sort of change the state based on the measurement results. And so we can use that to alter the arrow of time. So we can use that to alter the arrow of time so it effectively takes on a value that's sort of stuck at 0. so that it looks like just unitary measurement, unitary evolution. Or I think we can do that in ways that causes the arrow of time to effectively look forward versus backward. Some other kind of really creative projects we're doing is we can take all this data and then we can think about what would happen if we ran the feedback protocol in reverse. That is, if we did feedback results that anticipated what would happen next. And so we can sort of play around with the causal order of what feedback we apply and how does that relate to what measurement results we get. And so then you can think about time reversing feedback processes. And you can ask, how does that change the arrow of time? So this is actually a project that we've been slowly working on for many years, just trying to think about the role of feedback in these things and the causal order of feedback. And it's actually quite, it's maybe too rich of a problem because there's too many different ways to think about it. So we've had trouble tying it into a coherent publication, but it certainly gets interesting. I'll give you that.
Thanks, that's really interesting. Okay, so it seems like we don't have any other questions. We have lots and lots of thank yous and virtual claps in the YouTube chat window. But I think if that's it for the questions, then maybe we can conclude here and I can let you get on with your day. So I'll
thank you.
Say thanks very much to the audience once again for participating and tuning in, and especially thank you so much, Keita, for a really interesting talk. We'll be back again shortly.
My pleasure. Thank you so much for organizing this. It's been really great.
Thanks a lot.